Welcome to this lecture. This is the first lecture of week 7. So before going forward with the discussions of this week, let's first quickly recall what we have done in the previous week, that is in week 6. So we have defined the integration of measurable functions with respect to the domain side measure. We have also looked at some of the major properties of such an integration, and as an application we have obtained the expectations of discrete random variables. So that is in a nutshell what we had discussed in the previous week. Let's go forward and look at the slides of this lecture. In the previous week we defined the measure theoretic integration of real valued measurable functions, and as a particular case we also looked at the expectations of random variables. So this was simply the integration of these measurable functions with respect to the underlying probability measures. In this week we are going to study the limiting behavior of such integrals, and of course as a consequence we are also going to get limiting behavior of expectations of random variables. These results are now being stated for real valued measurable functions. However, if you can obtain the existence of the integrals, you can also consider these results in the extended real valued functions case, and using similar arguments you can extend or prove the results for these extended real valued functions. The arguments are identical and we are not going to separately state the versions for extended real valued functions. As long as you can define the integrals for extended real valued functions or you get the appropriate integrability conditions, you can prove this. Alright, but let's focus on one of the important steps that we did in week 6. We computed the expectation for discrete random variables, and what we had used there was that the fact that the law of these discrete random variables are convex linear combination of Dirac measures. So this was used quite significantly, and we had to therefore consider the integrals of the underlying random variable with respect to these different probability measures or different Dirac measures. Okay, so in many of the following arguments similar situations will arise. In that we have to consider that the integrals are with respect to different measures or different probability measures, but the measurable function or the random variable that we are going to consider remains fixed. Okay, so under this setup it's important to keep track of the underlying measure with respect to which we are doing the integration. Okay, so to clarify this or to keep track of this, we are going to introduce this terminology to highlight which measure we are using when we are doing the integration. Okay, alright. So in this lecture we are going to continue with the standard notation that omega script f mu will be a measure space. So that is mu being a measure on this measurable space omega script f. Alright, so what are these terms? So we are going to introduce these terms called mu integrable functions and mu quasi integrable functions. So what are these? So if you have a function measurable with respect to the appropriate sigma fields, you are going to say that this is mu integrable if integration of f plus with respect to the measure mu is finite and integration of f minus with respect to the measure mu is also finite. Okay, so this is exactly the integrability setup that we had considered in the previous week. We are just adding the measure in front of the term integrable. Instead of just saying f is integrable, we are now going to say f is mu integrable. Okay, so this is now highlighting the measure in question with respect to which you are doing the integration. And similar terminology will now going to be used for quasi integrability case, where integration of f plus and integration of f minus with respect to the measure mu are going to be considered, and if one of them is finite and the other is infinite, you are going to say that f is quasi integrable with respect to the measure mu, or you can use this shorthand terminology that f is mu quasi integrable. Okay, this is again the same terminology that we had used in the previous week, but we are just highlighting the measure now by saying f is mu integrable or f is mu quasi integrable. Okay, alright. So with these terms in hand, you can restate the results of the previous week, and that's what you should do as an exercise. try to write down all these statements by using these terms mu integrable or mu quasi integrable. Alright, so now we are going to look at the proof of the monotone convergence theorem that was left out in the previous week. So first recall the statement that you are going to consider a sequence of non-negative Borel measurable functions such that the function should be non-decreasing in n. Okay, and as soon as that happens, we had earlier explained that there will be a limit function which you call as h, and we had also mentioned that the limit function, being a limit of measurable functions, will become a measurable function. So therefore you can consider the integration of h with respect to the measure mu. Now since you are given this functions hn, you can also consider the integrations of hns, and we are going to say that integrations of hn increases to the limit value which is given by integration of h. So that was the statement of monotone convergence theorem. So before proving this, a couple of comments that we should be aware of is that the functions that we are using here in this statement are non-negative, and hence you have the existence of all the integrals. Okay, so these integrals will exist but can take values as infinity. So the values, possible values of these integrals are close 0 to close infinity. Okay, so this is the range of possible values. Great. Next thing that we have to be aware of is that there are these comparison type inequalities between the functions. So for every fixed n, hn is less equals to hn plus 1. So therefore corresponding integrals will also follow the same order. Okay, so integrals of hn with respect to the measure mu will be less or equals to integrations of hn plus 1 with respect to the measure mu. But h being the limit of all these non-decreasing sequence of functions, you get that h is upper bound for all these functions. So therefore you also get the upper bound for all these integrations as the integration of h. But since these quantities, integrations of hn, are increasing in n, you therefore get the limit value, and as per these inequalities you will immediately claim that the limit of integrations of hn will be less or equals to integration of h. So that is a very simple inequality that is just going to follow from the original inequality that we just mentioned. Okay, but what the monotone convergence theorem is saying is that in this inequality the equality holds as long as you are dealing with this non-decreasing non-negative functions. Okay, so non-decreasing in n. Great. So that is the statement of the monotone convergence theorem. Alright, so let us see how do we prove this statement. So start with any simple function s which is approximating the function h from below. So what you are going to do is to choose this simple function below h. So since h is non-negative, you are just going to choose these simple functions between 0 and h. Okay, and for the purpose of our argument, we also need to fix a scalar alpha between 0 and 1. So you will see the usage of this scalar alpha. But use these two quantities, the function small s and the scalar alpha, to write down this inequality that alpha times small s is less equal to small s, and of course the small s is of less equals to the function h. Great. So you have these inequalities. So what we are going to do is to consider the integrations of this but on specific type of sets. What we are going to do is to now bring in the functions hn. So the functions hn increase to h pointwise. So that is the definition of h anyway. So you can consider these sets an. So for every fixed n, consider the set of points on the domain such that hn omega exceeds the value alpha times s omega. Okay. So what is this? Look at the sequence of values hn of omega. They increase and increase to h of omega. So therefore in this inequality, what is going to happen is that hn of omega is increasing and increases to the value of h, right? So therefore it will cross the value alpha times s omega at some certain stage. So we are going to consider that specific event. So this is what these events or these sets are keeping track of. We are going to look at these points omega such that hn omega has crossed this value alpha times s omega. Okay, but now if you let n go up to infinity, you will immediately say that hn omega, as they are approximating the value h omega, so therefore it is definitely going to cross this value alpha times s omega. So therefore these sets increase and increase to the whole set omega. Okay, so this is the increasingness in n. Now you look at every fixed positive integer k, you look at this quantity, that this limit of integrations of hn will be greater or equals to integrations of hk for any fixed k, right? Great. So that is just by the increasing property of the functions hn. But now look at these non-negative functions hk and multiply by indicator of ak. So these functions hk are of course greater or equals to hk times indicator ak, so you get this inequality here. But what is happening on these sets ak is that hk is greater than or equal to alpha times s there. Okay, so on the sets ak, the function hk is greater or equals to alpha times s. So use that and you get this relation star. So therefore limit of the integrations of hn has this interesting lower bound given by alpha times integration of the simple function on the sets ak. So this is what we have observed now. But in this inequality that we have obtained, the first term on the left hand side that you see is independent of the natural number k, and the term that you see on the rightmost expression, that is dependent on k. But here this ak is increased to omega as k increases to infinity. So what we are going to do is to look at the limit in this relation star. Okay, so look at the first quantity on the left hand side, so that is independent of our value k. So therefore you can just write this same value. So I have just changed the indexing from n to k. This is not a big change. So therefore this quantity, whatever this is not dependent on k after you take the limit. Great. But what happens on the right hand side? So the right hand side here will give you these limits here. Okay, so you are taking limits in k for the functions hk in between and then for the functions s here. Okay, so that's all you are writing down from the relation star. Observe here that the function s is kept fixed here, only variation in k appears through the set ak, right, and ak is increased to the whole set omega. Now recall the fact that for non-negative measurable functions, and in particular for non-negative simple functions, the integrals over sets give you a measure, and in particular this measure also is continuous from below. So therefore as soon as the integrals here that are being considered over the sets ak, these will increase to the whole integral because ak is increased to the whole set omega. So therefore here you have integrals of s multiplied by these functions indicator ak, and therefore they will increase to the integration of s here, and the scalar alpha just keeps intact here. Okay, so therefore you get the relation double star. This has been discussed in note 15 of week 6 about the continuity from below of this measure. Now observe that in double star the left hand side term is independent of alpha, and the right hand side the alpha is getting multiplied with the integral. So here the choice of alpha was between 0 and 1. If you now let alpha increase to 1 in double star, what do you get? You get that the limit of integrals of hk is lower bounded by integration of s. But this is true for all simple functions s such that 0 less equals to s less equal to h. Now what you can do is that you can choose to take supremum over the right hand side over all such simple functions, and therefore you are immediately going to get the inequality that limit of the integrals of hk is lower bounded by integration of h with respect to the measure mu. But remember that in note 3 we had mentioned earlier that hk's are dominated from above by the function h, and therefore integrals of hk and therefore the limits of integrals of hk are dominated from above by integrations of h. So therefore we already had the other sided inequality. Now put it together with the inequality that we have just obtained, and we are going to get the required equality as stated in the monotone convergence theorem. Great. So therefore we have proved the monotone convergence theorem. Now as an important consequence of the monotone convergence theorem, in week 6 we had mentioned that linearity of measure theoretic integration is true. Okay, and we had used that in our arguments. But now it is a good time to see the proof of the linearity or the additivity properties of measure theoretic integration. Okay, so let's quickly recall the statement that you are considering two real valued measurable functions given to you, and if it so happens that integration of f exists, integration of g also exists, and then you also can make sense of integration of f plus integration of g, then the statement says integration of f plus g exists and it's equal to the addition of the integrals of f and g. Here the integral of f addition with integral of g is defined only if infinity minus infinity does not occur. Okay, so that was what we had discussed earlier. Let us see how do we prove this. First, consider a very simple situation that f and g are non-negative and simple. In that case, we had already mentioned that f plus g is also non-negative and simple. Therefore, what you can now try to verify is that the relation holds, and that will follow directly from the definition. Okay, this you can take it as a small exercise, but it is just following from the definition of the integration as we had considered in the previous week. Okay, so that takes care of this simple situation. But then let's move ahead and try to consider the case when both m and g are non-negative and measurable. But recall, we had discussed earlier in week 3 that we can find sequences fn and gn of non-negative simple functions which approximates the functions f and g from below. So given any non-negative measurable functions, you can figure out such simple functions which will approximate the given functions from below. Here you are going to apply the monotone convergence theorem. You will immediately say that integrations of fn will increase to integrations of f and integrations of gn will increase to integration of g. So that's good. But observe that f plus g is also a non-negative measurable function, and fn plus gn are simple functions which pointwise increase to the function f plus g, right? So this is simply following the definitions of fn's and gn's, and therefore if you apply the monotone convergence theorem to this approximation now, you will immediately say that fn plus gn, if you consider the integrations and then consider the limits of that, that will be exactly the integration of f plus g. Okay, so therefore you get this equality. But then you had already mentioned that you can split the integration, you can write it as an addition of the two individual integrals when the functions are simple and non-negative, which is the case here. So therefore you split the integration here as an integration of the function fn and integration of the function gn. Therefore you do this, and individually these terms approximate the integration of f and integration of g. Just write that, and therefore you get the required relation. So you have now proved it up to the case when both f and g are non-negative and measurable. But the general case, it will be slightly more complicated. You will need to look at the positive part of f plus g and negative part of f plus g. But in general, there is a technical complication, which is the fact that the positive part of f plus g is not necessarily equal to f plus g plus. Okay, it is not really the addition of the two positive parts. Okay, so what is going to happen is that you will have to be carefully do the accounting for the positive parts and negative parts and get the required equalities. Okay, what we are going to do is to skip the explicit arguments. We want to reduce the technicalities. We are going to assume that this can go through for measurable functions which are now taking signs. But here you are assuming that the functions have integrals which exist. Okay, so for these cases you can do these approximations and get the result. Okay, if you are interested, please refer to theorem 1.6.3 from this book by Robert and Catherine Williams-Stead from this book titled Probability and Measure Theory. So this will be the second edition of the book published by Academic Press. Alright, so that takes care of the linearity or additivity of the integration, which was a proof remaining from the previous week. Alright, so now what we are going to do is to consider extended version of the monotone convergence theorem, which is also quite useful in practice. Again, we are going to skip the proof and we are just going to state this result, and we are going to use this. So this is being stated without proof. If you are interested, you might also going to look at the book mentioned above, the book by Robert Ashe and Catherine Williams Stead, and you have to look at the theorem 1.6.7. Alright, so what is this extended form? Okay, so in the MCT, monotone convergence theorem, we looked at the functions which are non-negative. So the functions already were bounded below. Okay, here what we are going to consider are some other function as a lower bound, and therefore you will have to put some appropriate conditions on that lower bound function. So you are going to consider this sequence of functions as in the previous case. So you will take h1, h2 and so on. That will give you the sequence. You are going to consider the pointwise limit as h as considered earlier, but now as a bound you are going to consider the function g. So there are two statements here. So if you have that hns are lower bounded by this function g, and if the integration of g exists in the sense that it's greater than minus infinity. So you are allowing the integration of g to exist, and you need the integral value to be not equal to minus infinity. So you are allowing plus infinity as a possible value. Okay, all right. So in this case, if hns increase to the function h, so it is approximating the function h from below, then the integrals will increase and increase to the integration of h. So that is the first statement. And the other statement which you might expect is the exact opposite relation is the case when the functions are decreasing. Here you will require an upper bound. Again we are writing it in terms of the function g. So if all the functions are upper bounded by this function g, and if the integration of g is avoiding the value infinity, so here integration of g can take the value minus infinity, but you are not letting it be equal to plus infinity. In this case, if the functions hn decrease to the function h, then you are going to get that the integrations of hn will decrease and is going to go to this value, which is the integration of h. Okay, so we have now discussed the proof of monotone convergence theorem, the additivity properties of the integrals, and we have finally seen the extended form of MCT, where you can use, instead of the zero function, you can use other functions as possible lower or upper bounds for the cases of increasing or decreasing sequences of functions. Okay, we are going to continue this discussion in the next lecture.